Hi, my name is Lisa Richter. I'm the Director of Industry Outreach and Growth for CSIA. Welcome to the Masterclass. Before we get started, a quick word about CSIA. Probably most of you here today are familiar with the association, but if you are not, all you really need to know is that CSIA's mission is to help SIs build better businesses. How do we do that? Well, for starters, we have a team of volunteer SIs who have crowdsourced a best practices manual to help SIs scale their businesses. In fact, the BP manual regularly reviews and updates the manual. Currently, it is on the sixth edition, and the committee is already planning for the next version. For those companies that want to take these best practices to the next level, CSIA also offers a certification program that includes a third party audit. Many companies find that this audit is extremely helpful for helping them understand their business and scale. CSIA is also helping system integrators grow their businesses with a new learning hub, which is an online platform with content and playlists that have been sourced and vetted by seasoned SIs to help our members get their teams up to speed quickly. In addition to playlists, users also have access to hundreds of hours of programming via Biz Library, including on topics like executive communication at an extremely reasonable price. With thousands of qualified integrators and suppliers, the CSIA Industrial Automation Exchange helps SIs, industry suppliers, and manufacturers connect and do business. For SIs and partners, it provides a platform to support your content and SEO marketing efforts, position yourself as a thought leader, and nurture prospects during their complicated buyer's journey. If you are not currently a member, now is a great time to join. Membership provides you and your entire team with a full lineup of virtual events and other resources from accounting to sales to operations to training, 365 days per year. It also means you and your team can attend the CSIA conference because this annual in-person event is members only. If you are currently a member, thank you very much, and don't forget to renew your membership. If you want to just get a flavor of CSIA and its members, I encourage you to listen to the Talking Industrial Automation podcast. CSIA members talk all things industrial automation, and it's just a great way to hear what your peers are up to. One last housekeeping note before I turn it over to today's speaker. If you have any questions during the presentation, please use the Q&A feature in Zoom. That just helps us stay organized. The session is being recorded, and you will get a link to the recording in the next day or so. At this time, I'm going to turn it over to today's speaker, Mark Bertrand. Take it away.
Thank you, Lisa. Yeah, welcome everyone, and thanks for joining. A little background on myself. So I'm Mark Bertrand. I'm a director for industry solutions at Smart Sites. I actually spent most of my career in the SI world. So over 25 years as a systems integrator. In fact, a couple of companies I work for were certified CSIA integrators, and it's a great program. Really helped us a lot on best practices and kind of building from a small company, with about 6 people up until it eventually became over 60 engineers. And a lot of that was, help from CSIA on scaling, growth, managing our projects and things like that. So it's a great organization. I was fortunate enough to reattend the conference for the first time in many years this past year. So the topic today is optimizing production using AI and machine learning models. We've been researching this, particularly around the ML side, for about 4 years now. Some of the stuff with the large language models that we'll talk about is relatively new, and that's a very fast evolving space. But I think everybody's starting to see more and more of this kind of baked into the major product stacks, coming out from like Aviva, Rockwell, Siemens. So this is definitely something that is evolving very fast, and really I see this as becoming very dominant in production management, optimizing production lines, production processes in the future. So the key points here that we're going to be talking about is first just a general review about what AI and ML are. They're interrelated topics. They're kind of like cousins, but they're not the same. And then how do you drive the improvement? So how do you really maximize these technologies to achieve objectives? And then how to get started, right? So if you want to start on this journey, as an integrator, you want to start providing these service offerings, because I do think there's a lot of revenue to be obtained in the SI marketplace. Building these models, training these models, and then educating customers on how to utilize them. and as well as service offerings that, once you've actually, got some output from these models on how you can improve, then actually implementing projects, which could be low cap or, major CapEx projects for your customers. So there's a lot of different kinds of machine learning models. We're going to focus on a specific class called boosting regression models. So these are similar in some characteristics to a linear regression model, but linear regression models are very limited. They basically plot a line through kind of like a point cloud. They really are not very good at handling nonlinear systems or multivariate systems. And when you start like looking at all these different machine centers on a production line, and you've got accumulation in between them, and the bigger these lines are, and the more accumulation, the more complex they are to optimize. And this is where these boosting regression models really shine because they are able to handle all these different variances. They're able to manage outliers to a pretty good extent because they build trees. So effectively what they're doing is they're building kind of related sets and organizing them into trees. And that's what allows the model to be able to say, all right, so there's an inflection point in a particular set of characteristics. They can perform predictive modeling, so they can make predictions. So we'll talk about some of the different types of analytics that come out of these models, but they can handle very complex relationships and make predictions that in our studies that we've done are very accurate. So we've, predicted, things like a 6% increase from the model, implemented a project, and then gotten like a 6.5. So we were surprised at how accurate. Maybe we're just lucky, but we've had some great results in terms of the predictive ability of these models. They can also provide descriptive and prescriptive. Again, we'll cover these a little bit more detail, but descriptive fundamentally is talking about like it actually describes your process, right? So it actually gives you like one of the big things we get out of a prescriptive analytic is what is the true bottleneck? And that's often been a surprise as we run these models because like if you think about like a packaging line, you always think about the filler as your bottleneck. And there's a concept of a V curve that's typically utilized where it's at the bottom of this V curve of speed to capacity. Um, Often we've run these models and found out that's really not the true bottleneck on the line. And the key thing here, by the way, on knowing your true bottleneck is what has the most influence on the overall output of the line and where to focus your energy. But one of the downsides of boosting regression models is traditionally they've been very difficult to build, train, and utilize. Requires like a lot of knowledge. I wouldn't say you have to be like a PhD in data science, but you would need to build a lot of knowledge traditionally to be able to handle these models. And just for reference, I am not a data scientist, right? We've actually got some on our team who kind of work the details here. So just a little precursor. If you ask me really detailed questions about these models, really technical ones, I'll probably have to punt some of those. But one of the great things that we'll talk about is how these have become much more accessible to, I'd say, you still have to have some knowledge, but you don't have to have the same level of knowledge you traditionally would have had. So in the contrast, what we hear about most in today's world, with ChatGPT and Gemini are really large language models or generative AI. Now, these things are incredibly powerful, right? So they are trained on enormous amount of data. And so like one of the fundamental things they do is they've got a natural language interface. So they can read text, they can interpret it, they can answer in a natural language. And they can also search vast amounts of data and kind of correlate that data and give you answers. So I don't, I'm assuming most of us have had some, kind of usage of these types of models before. And it's crazy how they can interpret images, do all kinds of different things. But fundamentally, they are very accessible, right? Because my kids use LLMs. They're everywhere. Some of the kind of pros and cons though is they operate over a context window, right? So they're really kind of looking over this one window, and they don't have a lot of memory, right? And what they're really producing is probabilistic outputs. So they're not as good as quantitative, right? So a machine learning model is very quantitative, right? So it's using actual, numeric data. Well, LLMs really look more along the lines of probability, like what is the most likely thing? Um, and one of the downsides of that is that LLMs will hallucinate. And so like one of the early studies we did with LLMs was, just kind of feeding like shift, data into there and say, give me a shift report. And some of the data that came out with was great, right? It came up with, tables of KPIs. It kind of automatically knew like to give us mean time between failure, mean time to repair. We were impressed by some of the things it did, but it hallucinated. It basically took one of the machines that had a corrupted data stream in it and said, this machine is your major bottleneck because it had zero uptime. And it basically said, you should replace this machine, and here is how much this machine would cost and how much the payback interval, the ROI on replacing that machine would be. Well, it's just going out there and scavenging industry norm data and trying to, give us this kind of prediction. Well, it has no basis, right? So that was a purely hallucination. So LLMs don't have good guardrails inherently. That's one of the big downsides is they will try and go out there and give you tremendous amount of outputs, sometimes not really knowing what it knows more than what it thinks it knows. And the other big downside is computing cost. Like if we were to try and productize an LLM-based optimization thing, we would have a very difficult time computing or calculating what our computing costs would be. So that's a big downside. Whereas machine learning models are much more compact, very, very finite computing cost. So that's not an issue. So what we've really kind of arrived at is it's not one or the other, but for the optimal effect, we want to combine both. So the idea is, to some extent, to take a machine learning model and wrap it with an LLM. So and one of the things we're able to do is we're actually able to use LLMs like ChatGPT and Gemini to create these templates. So create templates for boosting regression models. So it's kind of creating the basis of the model, which inherently gives it some knowledge of how to work with it. And then once we've built those machine learning models, and we have to do some training, there's some workload in there that does require some human interface. But now we can use the LLM to provide a natural language interface to curate and query them. And this is what makes them more accessible because instead of having to go into, some of these things like MATLAB has got this, there's some, third-party open source tools that we've experimented with. And again, they're complicated to use, they're complicated to interpret. But now the LLM can actually, give you a chat interface and you can ask it questions in a much more natural way. And then with additional training, they can now interpret that production data in the underlying model, and they can start creating new analytics and even, power recommendations. So, in an agentic architecture where you have different agents performing different things, you can have one which is kind of interpreting the model, one that's providing the natural language interface, and another one which is creating a recommendation engine, which can actually now look at data against norms and say, hey, you've got a problem over here, so do some anomaly detection, or even tell you, hey, that's likely due to, a given causality, like, poor material quality, something like that. So that's where we really see this going is not just, doing analysis and optimization, from more of a reliability engineering level, but also really looking at production data in, I wouldn't say real time, but a near real time context and saying, this is what you should be looking at, this is what you should be doing. That's kind of like, I think, a future state for this. So let's kind of, dive into how we actually drive some improvement. So how do we actually put this into practice? So first we'll talk about descriptive analytics. And as I mentioned, this is really kind of analysis of the characteristics of the line. So what they do is they provide these insights, and one of the things they do is it's called feature importance. All right, so feature is a kind of a generic term within machine learning models, but a feature could be something like rate. A feature could be mean time between failures. So it looks at these things, and it could also be machine center. So you can look at one of these values by machine center. So one of the first things we do is we kind of created a KPI of our own. And what it does is it takes availability times average rate. And we call that effective rate. So again, it's a little bit of a made up KPI, but the key thing is it's in an engineering unit. So it's really units per minute is what we're, kind of treating as our primary KPI, because that's the true throughput capability of that machine center once you've taken its availability, multiplied it by its average rate. And then, so the first descriptive thing we do in terms of feature importance is we look at which machine's throughput has the most influence on the overall line output. So the inputs to that calculation are all those individual unit op throughput rates. And then we're using as the single output the overall line output. So this is how many cases produced per hour. Sometimes we use the filler, but that's what we're using as the output. So which one has the most importance or the most influence? And so that tells us right away if we wanted to focus our energy, and it ranks them, right? So it's going to rank them in, kind of a Pareto descending order type of output. So it's going to say this unit op is your number one feature importance. That's where you should focus your most energy. And it gives you proportionality. So it's not just giving you a 1, 2, 3. You might see that two are very close together. So, unit op 1 and unit op 6 are, your top two, and they're very close together. Or it may be a big drop off. And then you can start looking at, sub KPIs. So, okay, within that throughput calculation, is it more rate oriented? Is it more, mean time between failure, mean time to repair? Which sub KPIs are having the most influence on that individual machine or the overall line? And what that's doing is that's now giving you the keys, right? So where if I want to start trying to tweak a dial with like, some type of, Kaizen event or some type of, even, kind of, line rebalancing, so rate optimization, it starts giving you the keys to figure out where to really start looking and acting. So here's a real world example. So we were working on a line that had these two machines, which were fairly close together. There was a bundler, and it was kind of wrapping units, and then it was going into a tray packer. Now, the tray packer had lower KPIs, and a technology that we're using underlying this is our Able technology. And one of its features is that it does a root cause algorithm. So one of the analytics that Able produces is it tells us, kind of ranked by machine center, which were the highest impact machines in terms of root cause. Okay. And we've known this, since we introduced the feature is again, the more complex the line, the more accumulation, the more parallelism, that root cause can get a little abstract, right? So, but the root cause was saying that the tray packer was our biggest cause of downtime for the overall line. Okay. But then the model actually ranked the bundler. So we thought, okay, so this doesn't seem right. We've got a discrepancy between these two outputs. So when we did some further analysis, what we figured out is that the bundler had a lot of very short stops. And what was happening during those short stops is there was not much accumulation between the two machines, but there was a lot of accumulation upstream of the bundler. And so as all those short stops would rarely fill up the accumulation, but it was degrading it. So over time, that accumulation is filling and filling and filling because it can't recover it, with overspeed. And then when the tray packer would finally fault, it's a corrugated machine, so it takes a little longer to repair it. So it happened less frequently, but it was a longer mean time to repair. Those stops would then cascade through the line, shut down the filler, and be reported as the root cause. So based off the way they approach it, both of the algorithms were correct. But what was misleading by the root cause is saying, hey, you should be focusing on this tray packer. We should really be focusing on the bundler. The action that was taken was we said, all right, so if we're degrading accumulation, one of the cures for that is to increase the overspeed capacity. So we basically had to bring both of these machines up in rate. And when we did that, now it was able to recover the accumulation more effectively and now start buffering out some of the stops from the tray packer. Because if the accumulation zone wasn't full, it had enough accumulation to absorb the stoppages on the tray packer. So we noted over after doing the retuning that the average accumulation upstream of the bundler was considerably lower, and the number of stops cascading through the line were also reduced, thus increasing the overall throughput of the line. So that was a positive win using the data from the ML versus the data we were using from more traditional analytics. So now we kind of move on to prescriptive and predictive. And there's a little bit of overlap. Prescriptive is like more what you should do, right? Predictive is more like a what if type of scenario on like if I did X, I would get Y. So boosting regression models, they can guide you through this process. So you can actually do things like, all right, and we did this in this previous example where we said, but what if we increase the rate? So what if scenarios changing a machine KPI? So what if we could reduce the mean time between failures, reduce the number or frequency of stops? What if we could improve rate? So in this case, we said, all right, and when you think about this sometimes, there's dials that are easy to turn, there's dials that are not easy to turn. Like reducing mean time between failure can be tricky, right? You could try different center lining, you could try different, CIL procedures, clean and spec lubrication to try and reduce those. But there's a finite amount because machines kind of have their characteristics. And, there can also be variability in material quality that can make it hard to adjust. But rate is often one of those things that, if you've never really pushed a machine, you don't really know what it can do. So that is one of the ones we tend to focus on the most is rate-based adjustments. So I already kind of buried the lead, I think, on this one a little bit, is that we reduced the number of, we looked at reducing the number of bundler stops, in which the model showed it would actually produce a major impact, but we didn't really think that we could adjust that. Hard to achieve in practice because, variability, material quality, but it also showed a very similar impact on increasing the rate. That showed an impact. So that's what we did. So we increased, and like I said, we had to increase both machines because they're fairly close together. Took a little bit of retuning to do this, but it wasn't a long process. I think it took just a few days of getting, some mechanics out there with some operators and really just kind of pushing this gradually a little more until we got to a level the model predicted. And we got, I think, within 1%, the amount of improvement on overall throughput that the model predicted. So again, it's very quantitative. And one limitation just to be aware of is that models can't predict things they haven't seen. They can do some estimates, but that's where things can get a little gray. If you're trying to do rate balancing, you might have to intentionally create some variability. Because if a machine always runs at a constant speed, the model's going to have a very difficult time making a prediction on what impact the machine's rate would have. But that's one of the reasons why we use average rate, because that creates some variability in those samples. So next idea is using an optimization algorithm. What if analysis can be a little tricky because sometimes like, well, what question should I ask it? Like what type of, variation should I use? The model itself is very good at it, but the process can be cumbersome and, sometimes it's a little guesswork, right? Which eventually you're going to get it right, but, why guess? So there's a type of algorithm called a Bayesian optimization algorithm. And what that algorithm is designed to do is specifically designed to test a model and then try to achieve specific goals. So the idea is you give the algorithm some type of goal, like maximize my output from this overall line. And then what it's going to do is it's going to start running experiments. And it looks like, it determines like the proportionality. Like if I adjust this one, it's going the right direction. If I adjust it the other way, it's going the wrong direction. So play with this. And so what it does is it runs through testing that model to see what it could do. And then it's going to come out with some outputs saying, all right, so these are my scenarios, these are some of my outputs. And then you can focus your what if on those specific things, dive into more detail. So this is a way of speeding up the process of doing predictive around these models. So one of the use cases is determine the optimal rates on a production line. And, there's different philosophies on this. Like I've had a lot of debates with, folks in production environments, they want to run slow and steady, some want to push the machines. Well, this really tells you which machines you should push and which machines you don't need to push. So that is a great way of, again, focusing your energy and then, putting that energy into the maximum impact. So it will find those optimal settings. And it doesn't mean they're necessarily achievable. You may not be able to achieve those settings, but it tells you what you should be shooting for. Next topic is kind of getting back into, so this has all been very focused on the machine learning models, what their capabilities are, how they're used. But now the idea is let's start layering in Gen AI, some large language models to build and deploy the machine learning models. So again, major barrier is the knowledge needed to build and interpret. I call that accessibility. They're hard to access. So Gen AI can help a user step by step to build a model, evaluate it, optimize. It does support, Bayesian algorithms, so you can actually layer those in. That's typically going to be a different agent, so you want to separate that in an agentic architecture to be something that runs separately. But once you've kind of built the model, and there's a I forget the acronym, but there's a way of describing an AI model that supports an agentic architecture, and it kind of gives you all the different primitives and how to look at that model. So once you've kind of wrapped that machine learning with that type of AI modeling, now these other agents can interact with it more effectively, and now they can start translating those predictions into some real insights. And it can build pipelines. So it can embed workflows. There's a lot of things you can do once you start layering that Gen AI. And I'll show this real quickly. I didn't want to get too much into this. Let's see here. I've got this abstracted a little bit. But this is something I did, just a very, very basic example. So this is just ChatGPT. So I just said, create a workflow, and I gave it a specific prompt. So just so you know, the machine learning technology we're using is an open source platform called Jupyter. So I specifically prompted it to build a workflow for a Jupyter boosting regression model to use production line data for optimization. And it thought for more than 17 seconds. That's why I didn't run this thing live. But it comes out and it builds this this model here. So it's saying this is what I can do, and you could actually download this Jupyter workbook right here. But I gave him one more prompt just to say, hey, let's tweak the column names, right? So I wanted the column names to be asset name, date, time, state, reason, duration. And it went in here and just kind of retweaked it a little bit, and even gave the header here, which is mapping those columns. And I'm not going to go through all the detail here, but it's telling me that it's actually going to parse it automatically into hourly panels per asset. It's going to compute downtime events, downtime counts, and it's going to basically build this workbook. Now, I'm going to just specify that these two simple prompts created a working model. It's very basic. It needs more refinement, but that's just a quick example of what something like ChatGPT can do to get you going. So how to get started? So, hopefully some of you are at least getting a little intrigued by this and saying, all right, so how would I get started? What do I need, right? So, little thing on this. Biggest thing is data. You need data, and that's kind of obvious. But the thing is, you need the right kind of data and the right quality of data, because this is where it gets very specific around garbage in, garbage out. If you feed it the wrong data, you're going to get the wrong outputs. So the best input is what we typically refer to as utilization data. So this is a data stream, which is a sequence of events, transitioning between different states, different reasons, and you need to have an effective state model, right? And typically what we're going to use on a packaging line is something that has running, block, star, failed. There might be some idle stage or some bypass states. The key thing is that when you're processing this data, some systems, some MES and OE systems only really look at uptime and downtime. Well, if you think about a machine because this is all using unit op data, you have to be able to exclude the blocked and starved states, right? If a machine is externally delayed, you don't want to treat that as downtime, right? Because that is going to give it a skewed set of KPIs for availability, mean time to repair, and mean time between failures. So it is very key that you are able to differentiate external delay states from the actual failures. Same thing with bypass situations. If you have machines that are used conditionally, you can't have them just reporting failed for an entire shift. It's going to blow up your data. It should have production counts. You can have defect counts. Machine settings can be a useful thing to include in your data stream if you can access those. If you want to do some center lining optimization, that's another big use case. You need categorical variables. So we talked about features. Categorical variables are ways of slicing or segmenting your data. Shift is useful. The big one is SKU, right? So if you have, and the thing about SKU is a lot of systems will kind of break that down by like an SAP part code or something like that. What you really want is things that affect the line or machine performance. So if you have different bottle sizes, you definitely need to parse it by bottle size. If you have different pack out configurations, you may or may not want to have those in there. What's key about this is that, obviously you've ran two bottle size and you conflate those streams together, it's not going to be able to give you good outputs because it's going to be looking across these things. So they have to be segmented properly. But you don't want to over segment. So if you had like, 10 different part numbers for the same bottle size, well, now you're over segmenting. It's making you generate more and more data. So you need to do a little bit of abstraction there sometimes on how you map SKUs. Again, like shift can be very useful. We always want to have that if we can, because now you can start looking at, variances in shift performance or crew performance. Quality over quantity. A lot of people think you need, months or years of data to train an effective model. In some cases, you can have a few weeks of good data and you can actually get a model which produces good predictions. One of the things ML models do is they tell you how many samples they've built into trees and they use test cases. So it basically uses some of your samples as test cases against the model itself. And it tells you as the number of samples in the model increase, how the predictability increases. And what you're looking at when you look at this curve is it's going to start to flatten out. So what it's basically telling you is that, once you get to a certain point, you've got a pretty effective model. As you add more and more data to it, it's getting incrementally, more predictable, but you're in diminishing return. So again, don't focus on quantity. And one of the things on the flip side is that if you do use too much data, what you could have is like maybe you did an equipment upgrade within the course of this overall data set. Will that change the conditions of the line? So you don't want to use the data prior to that major change you made on the line. You want to throw that out because it's no longer useful. So too much data can actually hurt the integrity of your model. Data quality, again, very, very critical. Um, Boosting regression models are good-ish at correcting errors, but they can overemphasize outliers sometimes because those create like some additional trees that you really don't want within the prediction set. It doesn't take a lot of bad data to skew the learning process. So there has to be pre-cleaning on the data. Some of the things you do in pre-cleaning, because you're typically chunking this data, right? And our samples are a good benchmark. Really big lines, you might have to do larger samples. Because the idea within a sample is that you've got these KPIs, right, of all the individual machine centers and what the overall line output was within that sample. You need to see enough time. So if it takes, say like, for a lot of lines, it takes about like 10 or 15 minutes for, product to flow through the line. So an hour sample is sufficient for that. But if it takes like 45 minutes for, like product to flow through the line, you need to be going more to a 2-hour sample. So sample sizing does matter. It's a little bit proportional to the size of the line, but you need to remove like major downtime events. So if you had a major breakdown on the line that emptied out the line, you need to throw that data out because that doesn't represent typical or characteristic line flow. You need to throw out samples or clamp samples with individual large downtime events. Because like if you think about like a major stop being, excess of 10 minutes, you need to clamp that because one thing that we've noted is that mean time between failures has a lot less variance. Mean time to repair can have a lot of variance because of the fact that, we always capture a first fault stop. Well, that doesn't mean that it took that long for that fault. It may just mean that it took longer because the operator decided to clean the machine. So you see a lot of variance in mean time to repair. So doing a little bit of clamping and filtering on that is important. So you need to have a right, data stream with the right quality, and you still need to do some cleaning on it. Key thing is that cleaning should only remove a small percentage of the samples, right? So if your cleaning process is removing, like 25, 30+% of the samples in your overall data set, you're starting to really degrade the model. So you really need data that is, probably around 70% or better in terms of, the cleaning algorithm, how much it throws out. So key is you want to start with a very high fidelity utilization data stream, right? Because that's going to minimize your cleaning loss, it's going to minimize your cleaning time, and it's going to maximize the effectiveness of the overall model. So again, quality over quantity. And yeah, and cleaning, what I've said it on some of these sessions with like Mason, some other organizations, talking about like, end users talking about their AI journeys. And one of the things I heard over and over again is that it's hard to retain data science knowledge when these organizations because these professionals become very frustrated with the quality of their data. And they're spending most of their time cleaning and curating the data rather than building effective models. And a lot of times they're finding their data streams are unusable. They don't have the level of quality or cleanliness that they need to build models. So they're having kind of a twofold problem. One is that they're burning a lot of time and cost just on this cleaning process, cleaning up their data and making it usable. And then, of course, they're having a retention issue because this is not what these, high-paid professionals really want to do for a living. So that is a theme I've been hearing quite a bit in the market as I've been out there. So again, starting with the right data stream is critical. So in building standard templates, right? So, you don't want to reinvent the wheel every time, particularly if you're a large, dealing with large customers, you want to build templates, which can be organized by use cases. So, changeover optimization, line production. We kind of focused on throughput because we just don't have time to talk, but there's a lot of different use cases out there. Batch cycle time optimization. They should include the common features, things like that, SKU, shift, crew. And then, I mentioned this before, SKU can be tricky, right? So you may have to have some abstraction that doesn't over segment your data. And then sometimes like eliminating operations, right? So, one of the examples I throw in sometimes is stretch wrappers, right? So I'm not really big on including stretch wrappers in the availability models in general. We do them sometimes if we know they're going to be problematic, but they can add variability, but no real impact on output. So sometimes what you have to do is, and this is usually after you've kind of built the model, is exclude some machine centers, right? Get to a finite set that you know are high impact machines. Get those ones that are extraneous that could reduce the integrity of the model. Just throw them out. And it should be like a, kind of like if it's not clean, don't eat it. And like your mom said, well, if it's not clean, don't use it. So again, like not all, machines could actually have high impact. You may have to go back and clean up their data streams, but if that data is not good, throw it out for now. And again, we chat on this briefly, kind of looking, typically for 1 to 2 hour samples. It's not a one size fits all. This is in terms of the overall data you need. Like I mentioned, you can do with as little as a few weeks. Some processes are going to be more, particularly if you have high SKU diversity. So if you run a lot of different variants in your SKU, you're going to need more time because you need that 3 to 4 weeks on each SKU. I'm going a little quickly because I want to get to the Q&A session here. One other thing is that time span doesn't need to be contiguous. That's a mistake sometimes that people say, oh, like, we missed a big chunk of data for a couple of days because the data collection system was down or the line was down. It doesn't have to be contiguous. Again, you want to filter out major changes you've made to the line, but you can use data from, adjacent months or you can skip a month. Not necessarily ideal, but that's not necessarily a barrier. So kind of like I'll say a little bit of our shameless plug, we're going to have one of those. So choosing a partner, right? If you want to get on this journey, whether you're, I'm assuming most of us are here SI world, but there might be some end users here. You want a partner who has some background. And like I mentioned before, we've been working on this for a few years now. We've learned how to utilize data, particularly from our products or our product indirectly, because Able is a system that feeds data up into an MES stack. So if Able is acting as the data curation layer going into the MES, then we can use the MES data, which is going to be richer with more features within that data. But the key thing is that Able is designed to produce an optimal data stream. So to be used directly or indirectly, because it has this, kind of high fidelity, feature rich set for the data. It does the right state models. It was kind of built to do this. I mean, we literally built the product envisioning, machine learning AI use cases. It does have great support. There's a few different flavors. Like I'm primarily using XGBoost. I find that have the best results, but there's a few other ones in that same class. But it supports all the major boosting regression model types. And then we've got some pre-built templates. So we've actually got some templates in Jupyter, and we've got some cleaning tools. So some of those cleaning processes I mentioned, we've built some tools for doing that, cleaning that data before you feed them in to train the model. So we do have, this is not a product, by the way. And this is not something, when we talk about like these types of delivering these models, delivering these results, one thing I want to make clear is we're not currently trying to productize anything here. What we're trying to build is tool sets that we can give to our system integration partners, our technology partners, train them, support them, and have our partners deliver these results to the end user. And the biggest reason there is like we have some services within our company, but we're not going to train our service team on how to do this. And even if we trained our services team on how to build and interpret models and give actionable insights to the customer, we can't implement the types of projects to recognize the benefits, right? That's what systems integrators do because, if they say you need to rebalance this line, you need to retune the speed rates, you need to maybe, change how some of your accumulation works. Well, that's what a CSIA integrator does, right? You do those types of control optimizations. We don't. So the best way for us to deliver these tools and this value to end users is via partners. So anybody who wants to, follow up, I think my email was in there. We're happy to work with anybody, you know, in any capacity. So I hit my mark. I wanted 20 minutes for Q&A, so this is where I stop.
All right. Well, this is where I pop up out of my trash can with some questions for you. And forgive me if you have already answered them in this presentation. I'm not the best on the technical aspects, so here we go. You mentioned that LLMs can query ML models.
Yeah. So I've mentioned an agentic architecture, and I should probably clarify that a little bit. So the idea of an agentic AI architecture is where you've got multiple services. So it's almost like a microservice type architecture built for AI. So, what you have is you have one service which is kind of, wrapping the machine learning model. So it knows its language, how to query it. Now you have another agent, which is maybe your natural language interface. So it now, like if you ask a question, it's going to feed that. So it's going to do the language interpretation. Then it's going to feed that question over to the wrapper for the machine learning model. And it knows what types of things. So, if I asked it, what's the temperature today? Well, it's going to come back and say, I don't know. I can't interpret that. And then it's going to give you a prompt of these are some questions I can answer.
Mm.
And so that kind of helps you now interact with that model. So it's almost like, the model's been trained, the wrapper then trains the LLM on what questions you can ask, what questions you can't ask, and it prompts the user how to interact with it.
Got it. So you talked about optimizing production. Can this be used to optimize other things like quality?
Yes. Like if you track defects, one of the notes in there was, we obviously want production counts because that's key to determining output. But if you're also tracking defects at key points, then you can also use those at outputs. So if you have like check weighers or, different types of inspection equipment with rejection, you can then use those as the output of the model. And you can use things like rate, for example. So there could be a very simple predictor where you do so like if you say like say a labeling machine, right? And you've got a label inspector that can reject poorly labeled units. What you could do is because one of the barriers sometimes in increasing rate is you say, well, if I increase rate, I can increase rejection. Um, so to find that sweet spot, that inflection point, what you do is you vary the rate of the machine, you track those rejections, and then you feed that into the model. And now what it's going to be able to tell you is how much impact rate has and where that curve starts to inflect, where, increases rate really start to significantly increase the number of rejection. And that lets you optimize both the rate of the machine and then minimize the amount of rejected product. So yeah, there's a lot of different use cases around quality, set point optimization. So if you have center lining or set point data, you can look at those factors in terms of the two big things that center lining and set points affect are quality or rejection, but they also adjust the mean time between failure, the frequency of stops. So, if you're, changing different settings suboptimally, you're going to increase the number of stoppages, reduce your mean time between failure. So yeah, there's a lot of different use cases.
So, final question. Are there uses for AI or ML in daily activities like tier one or tier two meetings?
Yeah, so that's actually one of the active work streams we've got our team working on is we're trying to look, so, there's traditional like shift reports or daily production reports that are used in those tier one, tier two meetings. But one of the problems is that people tend to look at it from a very high level, right? They understand the overall line outputs and some of the major causes of downtime, but they don't have a good sense of what unit op level data is, right? So they're typically not looking at that unit op level on a daily basis or a shift basis. So the idea that we're kind of postulating and working on is if we can kind of baseline, all right, so what are the behaviors of these machines for good runs, right? So where does a labeler need to be performing? Where's the case packer need to be performing for optimal performance? Kind of set those ranges. Now we can start in these reports benchmarking these machines effectively and saying, okay, so not just did you have kind of a not so great production shift or day, but it was because the labeler was suboptimal. Because like when we do like Pareto charts of downtime, it's not going to factor in things like rate. So if somebody like turned the rate on the machine down, that's not going to show up in your production report. But if we're able to look at that machine's detailed KPIs and say this was a cause of your poor output, that gives you more actionable intel on a day-to-day basis.
All right, so pop quiz. We had some more questions come up in the chat, so get ready. What what would be your thought on if you had a critical machine that you were looking at with predictive analytics in an effort to improve efficiency? However, this particular machine and the performance was based on the weather or seasons due to humidity, dew points, etc. How would you suggest evaluating? This is like one of those giant math problems, word problems that you got to try and suss out. It is in the chat if you prefer to like read it versus me saying it.
Yeah, no, I think I understand the question. So this is where we get into categorical variables, right? So I mentioned the normal categorical variables that we deal with are SKU and shift. But let's say relative humidity. Like I used to do work in brewing, and so like relative humidity was a big topic in adjusting the pasteurizer BOT, the bottle out temperature. So this is where you would want to feed those into your data stream. And those don't necessarily have to go into the utilization table, right? So what you can do for something like that is if you have some type of trend, right? So and you could download this, from a sensor in the plant or maybe just like from a weather service or something like that. And what you can do is then marry that data. So you take your utilization data stream and it has timestamps. And so you basically say at that timestamp for that sample, all right, grab the temperature, relative humidity, da 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 da, those categorical variables. And now that enriches your data stream, and then you feed that data stream into the model. And of course, you have to add those categoricals. Now you can look at relative influence of those things on specific outputs. So again, that could be looking at, rejection. So like if relative humidity, like you're using like older adhesive based, like glue systems for label application. Now you can look at the effect of that. You can also look at the effect of different settings at different, RH or temperatures. So you just need the data. And so just add more categories and now you have different influences on your outputs.
Okay, so now really this is the final question. How much pre-work do you spend with customers on feature engineering, or do they typically come to you with those determined?
Um, may not be understanding the question. When I think about features, I think about like, these are kind of like the KPIs, right? So these are different things that influence the outputs that we want. We're typically using a very finite set. And like I mentioned before, the big one we deal with is called effective throughput. So that's the first one. It's a KPI we kind of calculate, and it's usually in units per minute, units per hour. It's kind of a rate-based thing because that's how we're measuring output. And you definitely want some alignment between your inputs and outputs because things can get a little squirrely if you have different units of measure and things like that. So a lot of what we're doing is we're kind of using the typical data that we produce from the Able product, which has all those features baked into it. So we haven't really gotten into detailed feature engineering with customers, but if they wanted to do something a little different, like batch cycle time, we've just started working with batch cycle time optimization as a use case. That's where we would have to get some additional feature input because batch cycles can be they typically have a fairly distinct, like you're in a make cycle, then you're in a like a discharge cycle, cleaning cycle, but there can be variances on those, so we might have to do some feature engineering there. So hopefully I addressed the question. If I answered the wrong question, just let me know.
Yeah. Well, your contact information is here. So for the person who submitted that question, if that wasn't what you were asking, feel free to contact Mark. I'm sure he'd be happy to discuss it with you at some other time. But for now, I think we're going to wrap things up. And my colleague, who is behind the scenes helping me with this thing, she's going to pull up my last slides for me because on behalf of CSIA, I would like to thank our speaker, Mark Bertrand, for this informative discussion, and also thanks to Smart Sites for sponsoring the event. And of course, thank you for attending. Be sure to bookmark the CSIA events calendar so you don't miss any upcoming events. And that's a wrap. Once again, thank you for joining us and have a great day.